Hey everyone, and welcome to this talk on floating point challenges and how we can overcome this in Rustlang. Um, I'm my name is Prabhat, and I'm just 23 years old. I'm like aspiring. I'm just getting started in this industry, and I came across a lots of problems while I was working in Rustlang, specifically with floating point numbers. But before all of this talks, let's get some more info about myself. So that's me here, as you can see. So talking about some of my interests, they are like I love Linux, okay, and I like systems programming. Also, I like to music and DJ a lot. Additionally, for some physical activities, I like cycling as well. Apart from that, talking about my professional experience, I have done multiple programming jobs, freelancing ones and otherwise, during my college years, specifically in the domain of systems programming, which involved dealing with C++, Rust directly. And I've contributed to some open source projects in Rust. Some minors contributions are there, but yeah, I did that as well. And recently, I completed my internship as a Rust developer for a startup known as Aftershoot. It's one of the world's most thriving AI photography startup in the domain of photography. And that was some of details about myself. Also, if you want to reach out to me, you can have my LinkedIn is in the right top hand corner, and along with my GitHub, so you can scan it, reach out to me if you have any questions about this talk. On that note, let's proceed to the next slide. So all of these are the things that I'll be covering in my talk. Before designing the content for my talk, I kept in mind that the approach that I kept in mind was I won't be getting too much into the details about every single thing, like because you can easily find it out in the web somehow. But my approach would be to instead just give you a sort of like indicator on where you can look out in case if you get stuck, or what are the issues that can come along the way if you are working in with floating point numbers, specifically if you are in Rust. And all of these concepts would still be applicable for the other languages as well, that being said. But yeah, I have specifically kept Rust in mind, and how we can use Rust to mitigate these issues. So going back to the proceeding to the another slide, I would first like to give you a sense of idea on why the importance of floating point numbers is so much. So here's one basic example on what happened in the year 1991. So there was a Patriot missile system. We all know that U.S. has lots of different kind of weapons in their arsenals. So the Patriot missile failure, which occurred in the Gulf War, was again the result of some floating point calculation errors. And this was interesting because instead of like having F-64, some other type in their embedded architecture, which drives the missile, which guides it from one direction to the other, on where to, and it guides them on which location, target location of the region it should drop. There was some calculations there in that, and this error was in the 1/10 of a second. So, since a missile also carries an embedded hardware in itself, that needs some programming. And there was an inappropriate use of data type which couldn't accommodate the precise value of the 1/10 of a second, which resulted in gradual accumulation of the rounding errors over time because of the limited precision, which we'll take a look about in the next slides. And so because of that, rounding error propagation came in picture. We'll also take a look on this one as well. So the Patriot's tracking radar system relied on the time calculations, precise time calculations, because of such a high degree of precision. About 1/10 of a second has to be maintained to make it drop to the desired location. That didn't happen, and the result was there was casualty about 22. We came out with 22 casualty of 22 soldiers or something. I don't know the exact numbers here. But that was the result. Like, it dropped to totally another region. It drifted off from the target region out of somewhere else. So this can be the significant impact if things are not followed correctly, because implicitly we might tend to think, okay, why not just use integers, why not just use any other data types, but skipping something is necessarily doesn't means it's a solution as well. So let's go to the other slides. So these are some of the preliminaries we need to know before we get started to know about it. Just kind of like a quick note. So real world representation, the point of the floating point numbers is to provide a real world representation of the real numbers. So the numbers which contains decimal places. That's the fundamental purpose of any floating point number in any language, in fact. And they are used for scientific notations. They are represented in a form of through the scientific notations. Also, they have precision and the range thing in them. So floating point offers like a trade-off between the precision and the range suitably for a wide spectrum of numerical calculations. We'll understand this as well in the further slides, like why does it happen specifically, why there's a trade-off between the precision and the range. Also we'll take a look on limited we covered about limited precisions here, and also we'll try to understand the mitigation strategies, like how developers can apply mitigation strategies to manage rounding errors and ensure reliable results are being there in their code and doesn't cause any havoc. So let's start, like, how is the floating point numbers are standardized. So IEEE, or the Institute for Electrical and Electronics Engineering, 754 standard is like the widely used specifications for how a floating point numbers should be represented using the scientific notations. So all the things like operations, arithmetic that are being carried out is being defined by the standard. Also, this standard defines several formats for representing numbers in the precision thing. So we have different kind of precision range depending upon the powers of 2. So 2 to the power 5 or 32 bits here represents a single precision, and 2 to the power 6 is they're reserved for double precision. We'll understand this in the next slides. And extended precision is like for more higher. These are more specifically used with supercomputers, where we require more higher degree of precision values. So let's start by taking a look onto the precision. So single precision, or 32-bit in IEEE 754 single precision format is composed of, like, or rather I should say is divided in different in summation of different sets of bit. So the first bit here represents the sign. If the first bit is 0, it is for positive, and if it's 1, then it's negative, according to the scientific notation. And 8 bits here represents the exponent, so the power of tens, that's responsible for representing the decimal point value, decimal point in the entire numbers. Another is, this one is the most critical one, and this is significant bits. So 23 bits here are the ones that actually represents a value in it. So 2 power 22 is the range that which you can have your numbers represented, along with the help of the sign bit that represents whether it's a signed value or non-signed value. So we don't have like a binary division of the 2 power 23 from 2, which takes up a divided range. We don't have that. We have just positive values from the significant coming, and then we take a signed bit to represent actually whether it's negative or not. So here's a formula. I won't get into the details of the formula, but just for the sake of thing, I've put it here. Going to the next one. So also we need to take a look into double precision as well, because these two are the most used one in any in any programming job. So double precision in the IEEE 754 contains similar thing, but with enlarged precision and range. So of course, in any floating point number, the first bit will always be reserved for representing the signed or the unsigned status of the number. The exponent bit here will gonna represent the exponent part of the floating point number, and the significant bit will represent the the significant part, or the mantissa, which we better know as. So here you get more range and precision. So coming to the actual visual representation, so as you can see, this is there for the single this format here is for the single precision, that is 32 bits one. So as you can see that as per the previous slides, the first bit is reserved as the sign, and the rest, and the exponent one is used to represent the exponent part, which is the power of the 10 in the decimal number system. And the fractions here represent the actual number which will be represented from it. So the significant component here will be represented by the fraction part, which is composed of 23 bits. Multiply that with the exponent with the base of 10, and you get a scientific notation, which can be where a decimal real number in a decimal system can be represented using a number in a base 2 system. So that's exactly the structure of how it has been devised by the IEEE 754 standard. So that's where we're going to take a look at mostly. So again, we covered this as well, I think. I'll just go through it quickly. So first of all, there's a couple of things you need to have about floating point numbers, that is important things, or rather the issues that can come up while you're coding it out. So this is a drawback, somehow we can say, that floating point numbers are like they have a limited precision and rounding errors problems. So since the number of bits which are available is finite, so like representation of the real numbers often cannot be done exactly. It has to be like it can be done to a certain range only, because there's certain number of, we don't have infinite bits, we have limited number of bits, we have finite bits, so we can only represent it on a certain range of values, which we'll take a look on that in the examples in the slides. So this inherent limitation leads to rounding errors. So what we need to do is, like, since if let's say any number is way more long than in the decimal number system, then we need to round it off to represent it to the closest value possible in the given in the given number format. Like if we have 32-bit single precision floating point number, then we have to make sure that we round it from the significant component so that it can be represented properly, and we try to minimize the loss. This is like inherently present. So there are certain addressals regarding this limited precision thing. So let's start to talk about the problems, or rather the issues, one by one. So limited precisions and rounding errors, right? So every floating point numbers, as I told you previously in the previous slides, have a finite number or a finite number of bits to represent a significant or a mantissa here. Now, rounding errors will happen when the real number cannot be represented exactly. So the term real number here must be understood as like, this applies both for rational numbers and irrational numbers. So something that terminates well and doesn't, the numbers which make sense are the ones that are rational. They're usually finite and terminating, whereas irrational numbers are non-terminating. Like one prominent example is pi. So pi is an irrational number which is non-terminating and non-repeating mostly. So here, as you can see in the illustration given below, is like the green boxes represents the finite number of bits we have in any given precision type, and the rest of the red boxes here might indicate that those particular bits can't be accommodated here. So the entire bits given here in the top are the actual numbers, but since we have limited number of bits, we have to we have to round it to represent, since the red boxes is the ones that we don't have in our precision range, so we can't represent them. Now here's one common problem with it. So let's say if you have two floating point numbers, this is quite common, I'm sure many of you might have come across it already. So if you have two floating point numbers, the chances are that it might not output you 0.3 exactly. It might output you 0.3 0 up to 9, something like that. So because of this, lots of issues they happen. So to address it, we have fixed point arithmetic. So we can use numbers to represent them as a scale integers to avoid precision loss. One step could be taken like this. Another could be like we can perform arithmetic operations on scale integers to maintain the precision. So it's like you can you do not need to directly use the floating point numbers in the first place. You can rather use arithmetic operations on this on the scale integers, which will always be precise and return you the results. And you can apply some operations which will result to you which will help you preserve the accuracy of your calculations. Another could be to use a big decimal libraries. So this is also a advanced approach, but it is quite useful. You can Google up more about the big decimal here. I won't be covering it in more in lots of detail here, but you can use like numbig integer crate and rustdeck crates for arbitrary precision decimal arithmetic. And obviously one more choice which we have left here is a trade-off between the memory and the precision kind of thing. So you have to make a choice between F64 and F32 wisely, depending upon what your requirements are. So you have to go through that. Coming up to the another one is the rounding error. So since we have limited number of bits, as we talked about, because of that, this comes another interesting issue is of rounding errors. So we try to round it to represent to the closest value possible, just like let's say we have 0.3222 and non-terminating, but we have to represent it up to the fourth decimal place only after the point. So we might write like as 0.03222 and 5 something, or maybe 0 could be there. So that's what the meaning of rounding is. So precision loss can happen because of that, because of the rounding errors, since not real numbers cannot be expressed exactly using the limited precision here. And because of this, rounding errors can accumulate as a result of approximations made during the arithmetic operations. So let's say you have a complicated expression statement which has like lots of different mathematical operations present with itself, and what will happen if like certain expressions, certain components of those mathematical expressions will gonna accumulate more error than you might think of. So hence, what the consequences could be that it can lead to discrepancies between the expected mathematical results and the actual results obtained when using floating point numbers. So you can have like redundant error being thrown out in your calculations, which is very undesirable considering if you have some kind of applications where you desire precision. So here's one example of it. As you can see, there's two number x and y specifically being represented using the exponent part, e to power minus 15. And when we sum it up, you can see that you can see that this thing is not very suitable. Not giving out the results which we actually desired for. So to solve this, we have something like we can use a decimal types to work with. So Rust decimal crate provides that. It's similar to the numbig crates that we previously mentioned here. So we can with that we can work with the decimal based arithmetic, which can minimize the rounding errors. Also we can try to round only when necessary. Another thing is avoid cumulative rounding. So you can structure your calculations in such a way, if it's long, in such a way that it doesn't result in cumulative errors. Rather, it's like done in a way that avoids it in the first place. Also, one very good technique to overcome it is avoiding divisions. So mostly it's been seen that it tends to happen more with the divisions, because division, we have more degree of numbers represented. We have more degree of numbers generated while we are applying division operations. So rather it can be instead done using with multiply and then carrying out the end result. In other words, trying to minimize the division here directly if possible. Another good approach to rounding error problem is to use interval arithmetic. You can Google it up to learn more about it. So using interval arithmetic libraries, there was one Inari. Yeah. So Inari crate in Rust provides you with the interval arithmetic operations that you can apply in your calculations, so that you can have some loss prevented. Coming to the next point here is or the next issue is the loss of significance. So the loss of significance is because of the consequences in the limited precision of the floating point representation, again, where the available bits are allocated to the most significant bits. So the difference between rounding error and the loss of significance is that we just take in the most significant bits in a given binary number, and because of that we have something like loss of significance. They're quite close with each other, rounding errors and loss of significance, but rounding errors are something which we do explicitly, whereas loss of significance is something which is, again, not in our hands directly. So it can take place, let's say, due to nearly equal numbers, like if they're being subtracted, and hence the cancellation or the difference here can be completely avoided, resulting in something which is not very precise. So as you can see on an illustration on this slide, that we have two different bit blocks here. The first one is in the orange and the another one is in blue, and the third row is something which we see as a result that after subtracting it, if we had more numbers than we expected, then the rest of the ones which are in the three red boxes would get discarded, simply because we don't have range to accommodate it, and we'll take out the most significant bits in the given binary numbers. So for the significant or the mantissa part, so this can result in that. So as you can see, here's an example illustrating this. So we have two numbers which are quite close with each other, like the difference is not huge, but what you will see in the output here in the difference is that it will have something like 0.000899999 or something. So again, it won't be direct and very precise. So solutions for mitigating this one is, again, quite clever, like reordering the operations. So let's say if you have subtraction in some early in your complex calculations, you can restructure it down so that it can be done later on. If not later, and if it cannot be eliminated, then at least it can be done later. You can use alternative formulas to rewrite your entire expressions. One of my personal favorite ones is this is something which is taught to engineering students in their first year of the college, like Taylor's expansion. So Taylor's expansion is something you can learn more about. I won't be able to cover it here. So basically, Taylor's expansion is a mechanism through which you can precisely compute the number of the number of decimal digits you would need. It can go as long as you might want it to be. So it's kind of a formula in itself, and this can be used to represent any complex calculations in a discrete fashion. So let's say you want to approximate sine x, you can do it with the Taylor's expansion. You want to approximate cos x, you can still do it with the Taylor's expansion. You want to approximate tan inverse of x, you can still do it with the Taylor's expansion. So yeah, this is one of the very clever techniques that we can have for loss of significance to be avoided. Excuse me. And another one is to use arbitrary precision arithmetic, the one which we saw in the case of limited precision ones. So you can still use these grids as well if you require it. Now, coming up to the associativity, the issue of associativity and the order of operations. Now, this is quite interesting. Most of us are quite aware about the rule of commutativity for summation and multiplication. So most of us might not notice the difference here, that for the result 1 and result 2, the output must be the same, right? Most of us might assume that in looking at it in the first place. But the thing that is behind the scenes is applicable is floating point operations are not always associative. In fact, because the issues which you talked about previously, like limited precision, rounding errors, and loss of significance. So changing orders can lead to different results. It's quite possible. So you can run this code, you can find it by yourself, that it might result, if in the first case it will result to you, though we are doing the exact same thing mathematically, but the output which we're getting in the result 1 variable is 1, and for the result 2 it's 0. So this is very much undesirable and something we want to avoid at all costs. Now, the overcoming this issue could be done using the solution to this is pretty straightforward. So we can use parentheses and explicit groupings, just like in the case where we do it with the in the case of pointers referencing, where we have the scope of the evaluation to be decided using the help of parentheses. We can still do it using here as well, but we have to be a little cautious about it, because still it might not give you the exact results. But if you're aware about the order of our calculations in your expression, then this can be a good mitigation technique. And another one is reordering the operation, not just using parentheses, but you can also reorder the operation so that the loss of significance, the parts of the calculations where the loss of significance is the least, can come up before before the rest of the part where the loss of significance could be the most. So reordering your operations can be another good way of to deal with that. Another thing here is you can. This is very advanced, and honestly, I couldn't able to find lots of material about it yet, because probably this is still in the RFC stage of the Rust compilers. So you can use fuse, multiply, and add operations. So it's an SIMD operation specifically. If you don't know about it, you can still Google it up to learn more about it. But FMA operations can parallelize the certain components of the certain calculations of the component of the expression in a way that reduces overall rounding errors. So you can research about, you can take a look into this more in depth if you wish to. Now coming up to another interesting issue here with floating point numbers is comparison and the equality testing. Trust me, this one is the one which most of you will come across if you ever have worked with if you ever will work with the floating point numbers in your code. So I came across first time when I was in my high school. Like I couldn't compare the floating point numbers because the result was like it was so arbitrary that it was not possible for me to like write a code logic at that time. But coming to the point here, if you let's say want to compare two same floating point numbers, then it's better idea to use equality. Instead of using direct equality comparison, you can use epsilon based comparison for the approximate equality. Now, what does it mean? Basically, it means that as you can see in the function approx equal, we have two distinct floating point numbers, and we are first subtracting it, and we're taking the absolute of them because we don't want the negative results to be we only care about the magnitude of the result, not that the sign, whether it's positive or negative real number. So the thing here is we can compare it with the minimal difference of the epsilon, which is defined using the constant epsilon. By the way, standard library in Rust provides you with all of these constants. I've just written it explicitly for the sake of giving an idea of how exactly it is represented, but it's already there in the standard library, so you can directly import it from the standard crate. You can compare the result of the magnitude of the result. If it's less than the epsilon, then it's fine. If it's greater than the difference is greater than the epsilon one, then it's possibly not approximately equal to each other. So this one technique can be employed to test your code. To test like a floating point comparison. So getting into more specifics here, one we saw that you can use epsilon based comparison instead of using equality operator in the first place. Another good technique here is relative error comparison. This is very similar to the epsilon based comparison, but except the threshold of the comparison is something which we decide as a developer, having the knowledge of the system, that how much can there be a acceptable range of error difference. the acceptable range of the subtract the difference from two numbers here, which will be fine to describe it. Another technique we can use is units and last place comparison. So we can use ULPL equal functions to compare them in case we only want equality. This comes from the float compare crate in Rust, so you can use this one. It's quite good as well. I've used it personally. And comparing with some specific tolerance value. So this is again similar to the relative error comparison, but relative errors can be dynamic, whereas this can be static. So this technique can be used as well to avoid having some errors in the equality comparison. Now, another case, this is not a problem. Rather, this is like I should say, the specification given in the 754 standard of the IEEE that we can have not a number and infinity handling in the floating point numbers. Let's say that you want to divide two numbers, okay, and those two floating point numbers happen to be zero, absolute zero. Then in that result, mathematically, it should be nothing. So you can use you get certain methods, which is not a number method, which will result to whether it's number or not. If that's true, then result is nan, and result if it's infinite, then you can check for that condition as well. So these two methods are given to you so that you can check if, let's say, certain parts of your calculation might throw you like undesirable condition, and you don't want to write your own technique for like testing it out directly. So you can have this inbuilt methods to test it out for you as a safety check. And now, since these operations arise from division, all these conditions can arise from like having a square root of a negative number and something like dividing 0 by 0. So all these conditions where we can't express anything correctly. So in that, or the calculation might get into complex numbers. Means we should use these APIs to test whether this one is actually not a number or what. Coming up to the another one here is compilers optimizations. Now we are not excuse me. Now this is not an issue, but this is rather given to you as a safety net, so that you can deal with your compiler directly and instruct it explicitly not to like optimize or do some or to do some kind of a like premature optimizations during the phase of compilation of your code to executables. So compilers can optimize floating point calculations for performance range. So this can happen quite a lot of time, and may reorder or combine operations which may affect precision and could result in a associativity of the orders problem, which we saw in the previous slides. So to overcome that, you can use stable compilers flags to control those optimizations. So for example, here in this code, you can see that is one function perform calculations which take two distinct floating point numbers. And what can end up is it could be written as such as like it could be computed in a way such as b times 2.0, and then it could be added, or it could be previously added, and then it could be like multiplied with the 2. So I'm not saying that the order of evaluation is completely ignored, but how compiler is going to deal with such a complex expression is up to it. So you can't predict it almost every time. So it's better to use appropriate compiler flags to help it ignore it. So one of them is like inline never. So you are explicitly telling your instructing compiler to never inline this function call, and always let it be like computed once there is a value passed to it, because otherwise this can lead to undesirable output and accuracy errors. So some few compilers optimization techniques include like using compilers attribute. So Rust provides you with the attributes that lets you control the behavior of the floating point operations. One such attribute is target feature, and within this target feature you can have a parameter enabled that is a fast math. So it's going to do some internal instruction. It will release some internal instructions while compiling that this piece of code should have fast math support enabled. You can learn more about fast math like from the web. I'm not going to get into lots of detail, but fast math is basically something that allows you to like overcome the calculations that are arising from the compiler's optimization. Another thing you can use is use compiler flags directly in the phase of compilation rather than in the code base. So you can have a target CPU given, and you can use LLVMs arguments to enable fast math in your build file, so that since Rust is built on LLVM, so we can have a direct optimization option available from LLVM as well for the fast math thing. Now, coming to the accumulative errors, this one is pretty interesting. So quite sometimes, let's say that you might have to deal with some kind of series of floating point numbers. And in that scenario, it becomes quite necessary to know that there can be lots of, as we saw with the previous slides, that there can be lots of issues with the limited number of bits. There can be rounding error problems. There can be significant loss of significance, associativity, etc., etc. So because of all this, there can be an accumulation of the rounding errors. So it's like you're recursively calling a function, whether it's iterative or whether it's recursive or iterative, whatever. And because of a given set of calculations, that error will get amplified, or the range, or the entire period of the calculation. So to minimize that, we have something like Kahan's summation algorithm and compensated summation algorithm. So this one here is given to this one. The code shown to you on your slides is a Kahan's summation problem. It takes in like array of floating point numbers, which is a series of floating point numbers, and the output might not be the one, but since we are using Kahan's summation algorithm, we get a definitive result here. So you can use Kahan's summation as well if in case you're dealing with some kind of iterative algorithm which does a calculation of floating point numbers, or with the help of floating point numbers. Could be recursive as well. So we covered lots of things in this talk here. So I should so coming these two slides will be about summarizing it, like what we just saw. So excuse me. So first of all, naturally choose the appropriate data type depending upon the requirements, precision requirements. So go with F32 if you know that your range of calculations won't going to cross that boundary. Otherwise, you have to switch to F34 if you need more range and precision. Now, leverage some numerical computation crates for enhanced accuracy, such as rug, num, big int, dic. And in RE, you can take a look on these crates. These are great crates if in case you need to deal with some kind of floating point operations. You can use them directly. These are matured ones. Also, avoid direct equality comparison use with and instead use epsilon-based comparisons like relative ones and tolerance-based ones. Also, perform error propagation analysis to estimate potential inaccuracies. This is quite advanced. It doesn't employ use of any like library or crate or something, but what you can do is you can use some like way to estimate how much error is going to throw out if you deliberately put in some errors in your calculations, so that you can know how much errors can accumulate. Now, coming to part 2, you can consider using arbitrary precision libraries for critical computation of your code. So arbitrary precision libraries gives you more range to compute and more precision, since they rely on decimal-based calculations. So they will give you more specific results. Also, minimize accumulated errors in iterative algorithms. Use techniques like Kahan's summation, which we saw just a couple of slides previously. And also use stable compiler flags to control floating point behaviors, which can happen unknowingly, which can be done unknowingly by your compiler for you. So so you must want to avoid that. Also, thoroughly test numerical code with diverse input set. This is more or less we're talking about fuzzing testing, fuzzing here specifically. So thoroughly test numerical codes with diverse sets of inputs to identify adverse inaccuracies. So if you are not sure about certain edge cases, go ahead and put it there in your test cases, just to be ensured that unit test cases that once you're shipping out something to your production, it's tested and test proof, and you don't have something like a period missile crisis happening, in case you have to work on something like that. So that's all from my side. Like, I would thank you, all of you, for listening to me till here, this end. And yeah, if you, in case you have some questions, you can always reach out to me. I will be more than happy to answer whatever there, if and I will be more than happy to help you as well. So yeah, take care, guys.